much for this presentation. I heard you also say that the number of boats can really impact the river. Is that something that we should look further into? We've kind of looked at the type of boats, but.
So it's the number of waves, right? So if you have one wave against a boat, even if, one wave against a cross section, it's transferring, I don't know, however much momentum, mass and energy into this bank. And this bank can probably withstand one wave, maybe two waves. But if you put 100 waves on it, now you've both made the soil more wet, so those resisting forces are lower, and your dislodged particles, you've removed some of the material off the toe. So you're starting each wave progressively, like plucks a little bit more of the strength out of the bank. And then what happens ultimately is you get whatever that final wake is that really leads to a failure, and it kind of is that threshold behavior. So you'll see like these small changes, and then all of a sudden it becomes a sort of like the slumping failure that you saw like at the park, right? Like these block failures are cumulative effects of a bunch of waves. It's not just one boat coming through and hitting a bank.
And then another kind of follow-up is, I was with a boat, a resident of the river yesterday on his dock, and he said that before it was illegal to do so, people had put boulders up along his portion of the river, and that it's not allowed anymore, but that is right now seeming to stabilize the riverbank at his particular dock. And I'm wondering if you know who a good point person is to talk more about why that's illegal now to put boulders along. And it did seem to kind of create habitat. It probably has something to do with habitat. But who should I talk to? Hey.
It pushes the problem further. It just pushes the
It
problem
pushes
down
the
the
problem to the next neighbor,
Yeah.
is what it does. So there's a whole
Oh, okay.
part of that, and Randy Wildman might have
Again,
a
I'm
few
not
things
in front of
to
Lonnie.
say about that as
Okay,
well.
super. Thank you.
Yeah. And I just wanted to also add to what Representative Britton and Representative Neron is that this whole idea that, so the riprap or the rock protecting the shore, yeah, that works because, you know, we've been doing that for quite a while in Portland and in the most congested areas. But those of us who live there also create that barrier, okay? So our houses, your house, our boat slips, all of those structures stop those waves, not stop them, but they certainly reduce those waves coming in, I think, because we still have shoreline problems, but not to this extent. So
I'm sure Dr. Raymond will probably talk a little bit about this, but you're driving, instead of driving the car into the stream bank, you're driving it to the dock. And then what happens is you've got the junk show, right, where now all the flow is moving everywhere. It's a very chaotic flow.
yes.
And so you end up, in some ways, dissipating some of the energy because the car's crashing the dock instead of the stream bank, but it makes flows way more complex, so harder to predict what's going to lead to erosion. You may get flow concentrated in one area versus another, so scour. So it makes the problem way more complex, but it does reduce some of the energy from the waves.
And that neurotic, you know, strange pattern of wake and wave energy is what also causes all the damage, the property damage, and, you know, breaks boards away from things and pulls docks away from the houses and posts break and things like that. I'm starting to figure out why it's happening now. Thank you.
Yeah.
So you talked about a lot of variables, but can you normalize some of those variables and say, you know, in the winter, we've got two types of soil habitat, you got clay and loose soil, and, you know, I'm assuming the study will try to quantify the effects over time, but is there a way to identify what's a minimum threshold you should not exceed in order to retain riverbank and to stop erosion?
I think that, yes, absolutely that's possible, but there's going to be uncertainty in that, right? So we're going to go back and we'll say we can, I mean, and we absolutely can, and people have done this for other places.
You know, I used to work in tech, so we would make these assumptions and put them aside and agree that these are reasonable assumptions so that we can move beyond all the variables and talk about the real issue.
Mm-hmm. Yeah, it is, and it is useful to do that, but it won't definitively say that this property won't erode and this property will erode. Because there's just there's this environmental variability, which if you, yeah, so it absolutely is possible. And I'm not trying to discourage people from doing it, I think it's useful. But I think we should set our expectations that we can't reliably always say that, yes, this model, this statistical model is gonna predict what happens in a system where you've got, but one type of vegetation in one region, another type of vegetation. I mean, if you've been out there, you've seen it's highly variable in terms of the bank slope, in terms of vegetation type. It's,
I think on one side of the river it looks like this, and the other side of the river it looks like that. It's pretty consistent as you go through that. But, I mean, I'm trying to get to the point that we have a lot of river traffic, and I've noticed one thing, because I live on the river, is that these guys go out and wakeboard, and if they have more than one kid, the kid that wakeboards does his thing, or wake surfs does his thing, and then they're pulling tubes with these wake-enhancing devices in their boats all day long. So I've seen it with 5 boats, wake-enhancing boats, out from my dock at a time. That's clearly too much, right?
but then
What-
where's
what is
the
too-
line, right?
Right, what is the line? I mean, at some point you have to be able to say, there's some variability, plus or minus 10% we're willing to accept,
I
but
think it's way more than 10% is my point. And then how do you enforce it? Say your boat of, 10 feet, I don't know what the statistics are, however many.
usually 20-foot boats.
Right, okay, great. I'm used to ski boats, so I don't know about wake boats, but anyway, and then you have to figure out how to enforce it, right? So there's still both the science side of it, and then how does this local sheriff, whomever, take responsibility for making sure people are staying, more than 100 feet away from the bank, and they're going the right speed, and I think it's,
Well, I see them trying to do it now.
I've been out on the lower Willamette where they're, people are blasting through the wake zones, and the sheriffs are trying to pull them over, and they're just outrunning the sheriff. I mean, I'm not sure that it's that.
It's not being enforced, I can tell you that, right?
Yeah.
I mean, I see them try to. There's one guy, one boat out there
Right.
on occasion.
So I think that's the other half of the, which is not a science problem, but the other half of the conversation is to be, well, what is enforceable out
But
there?
I think we've got to talk science, then we got to talk policy.
Yeah.
Right? So you got to
Yep.
get the science figured out, so you can go develop the right policy.
And people have, and I can point out the studies like this one in Alaska, I think is probably the most relevant, which is why I keep referencing it, where they have created these policies and with mixed results in terms of its ability to prevent erosion. Yeah.
So if we're thinking about taking the first step, is it reasonable to assume, if we have to make a policy decision, that if you reduce the size and number of wakes, you can reduce overall the amount of erosion that's occurring? Is that a fair statement?
I believe so. I think Dr. Yim would probably be able to answer better, but I know the details of the hydraulics, the wave hydraulics, but yes, I believe that's an appropriate assumption.
Okay. So in terms of how we that have to make policy and these sorts of things go forward, it seems to me that's the position we have to start with, is that we know that the erosion occurs. We know that if we reduce the amount of, or the size and the number of large waves that hit the embankment, we can reduce the amount of erosion. And then if that is assumed to be a good thing, we have a foundation for making a policy decision.
Yes, I will say, and I'm going to keep coming back to this, but I will say the challenge is reduce it to what? So say you reduce the size of the wakes by half of what's needed, then you create this policy that's not effective. And I don't know what that number is, so I don't know, and I don't know if it's possible to pinpoint, we can only have 30 wakes of, 2 feet high before the bank fails. We could try, but there's a lot of uncertainty, so if we create a policy that says 30 wakes 2 feet high, and then the banks still erode, then people are gonna be upset, because both the people focus on erosion and the people focus on recreation, because we created a policy that.
That's more of a messaging issue in that nobody can assume that we will be able to create a perfect policy that will be perfectly followed. The idea is to have a policy that will at least reduce the damage as much as reasonably possible that is enforceable. But you have to have a foundation to start with, and that
Right.
foundation is it a good thing to reduce that
Yes.
erosion? And do you in fact reduce that erosion by reducing the number of waves and the size of those waves? If those assumptions are reasonable assumptions, again, you have a foundation for making a policy decision.
Yeah, I think there's a lot of interesting policy discussions that what we're learning here today can inform, but I think that I'm just looking at my watch here, I know we're about out of time, but we still have a handful of presentations ahead. No, I'm saying thank you for the science, but I think that I'm starting to hear a lot of like policy directed questions at the scientists, and so in the interest of we get to hear more of the science so that it can form our policy discussions that'll happen later. Desiree, thank you so much. That was fantastic, and I think you're incredibly impressive, and so thank you very much.
So I know that folks are going to be coming in with food, but maybe we should go ahead and get set up and get started.
Yeah,
So,
I think we should.
that's good. So who's next?
For you.
Oh, you're next? Okay.
No, that's our last. We can finish. Okay, so I am glad that the discussion went this way because some of the things that I want to address in this part of the presentation is related to what you just presented. And I'm sorry that you have to just
I know, sorry.
But you have to go to the doctor, right?
Yes, yes.
Good. So the fundamental, one of the messages that we just heard is that there is a lot of uncertainty and there is a number of elements that may be acting on this problem. And again, the question is like, oh, how we address the problem of the erosion back. So the first statement or the first thing that we are listening is that there is kind of no question about that there is an erosion produced by the wake of boat wrecks. And I hope that everybody acknowledges, including the people that is not right now here, which is the industry. So if everybody acknowledges that there is an erosion because of the weight, the zero solution is eliminate the problem. So there is no boat in the Willamette River, and there you go, you're fine. So that is the first question. I mean, I know, that is, I'm being stressed. No, that is the zero solution. Eliminate the problem from zero, there you go. We cannot do that because there's a number of other laws and policies that are in place, and we cannot prevent that to happen. And actually, we have other interests involved in this thing. So the question is, can we identify what are those thresholds that we can say, okay, we can limit the erosion in some parts, or we can reduce the erosion in some other parts if we understand the problem. And now we go into the details of what we are looking in this particular area. And we have seen there is some uncertainties and variabilities in what happens with erosion, and there is a number of reasons why, and that's what I'm going to just basically show you and try to give you a glimpse of how difficult it is to predict that, because it's in our particular place, and what I think it would be the next step on doing something, which is could be a combination of what we discussed, is a preliminary policy saying, okay, this is how we can do it, this is how we can reduce the erosion, and in the meantime, we do a thorough study on who and where we have problems. And we have indicated also, and I think that is another element that is part of the conversation, which is the protection of the banks, which is a not natural protection. So we are talking about riprap or sheet piling or whatever we do under the banks. That could be a solution. It is a solution. It is something that is done in navigation channels in other places, and that doesn't mean that we have that particular solution for every place along the river, but it could be a solution for certain places where we allow those boatways to happen. So we prevent the erosion of those erosions. And so let me also mention there is I would like to go through the understanding of the process, because that's how fundamentally us scientists go through these type of problems. We first understand what is the physics, so what Desiree just presented and other elements, and then we try to tackle the particular problem by knowing what's going on. So, and I think it's part of the discussion of the industry, the boat industry, is the argument that is that makes our position relatively weak. And we understand that both wakes are producing erosion. And part of that conversation says, oh, there is a natural erosion that is going to happen. And that is true. We have to acknowledge that there is also natural erosion. And I keep using the example, which was kind of nice, that happens this last winter. You saw how much river flow we got. And the amount of sediment that was transported during last winter as 2 orders or 3 orders of magnitude above whatever the boats are doing. That is true. We have to acknowledge that. We also have to acknowledge that meanders are natural systems that are going to be eroding over time. And the meander is just a natural process that when you have velocities, higher velocities in the outer part of the bend in comparison to the inner part of the bend, that produces erosion on one of the banks and accretion in the other part of the bank. That is also a natural process. And there is a number of probabilities involved in that process. But the scale of things is different. And I think that is the fundamental part of what we treat this problem. The scale means in time and also in space. So the scale problem of what happens with the boat wake is something that we can see in seconds, in hours. We see what a wake is doing to the riverbank just like that. And we have even videos and things to see that. What happens to the river in long term, which is the natural process of erosion of the meanders and sediment transport, happens in several months, years, or even more than that. And we don't have a good memory for that. So typically, it's difficult. People don't see that. If we see a process that is in the order of our age, so the human age, I don't know, 80 years, we don't notice, if it's beyond that, we don't notice the changes. We assume that everything that is right now is supposed to be stable and constant. And our argument on the wakes are producing erosion, and that's a major problem, falls apart immediately when somebody says, oh, there is another process underlying that is erosion because of the river, and that's a natural process, and we have to acknowledge that, and that makes the point weaker. So in terms of going into the policy, and again, I am not a policymaker, and I don't want to go that way, but in terms of policymakers, the message that we are sending is important in that sense, that we have to understand the process, give some physics and data, so the point of the policy is supported by that. If we keep on using what people knows or the observations or something that is not complete, it's very easy for anybody to just fall apart the whole argument. And that we have to be careful. That's where we are, that's how we enter here. As scientists, we follow a methodology, so there is no questions, there is no bias, there is no policy or interest related, we just give facts. And the fact is that, whatever, with the conclusions are given. So, this is a long introduction, but just to give you a little bit of the flavor of what I have. So, Desiree was very nice in showing us the uncertainty of all the processes. And the problem, what I find that is happening in this area, is that we have everything and more as a variable in this area. So everywhere from the Newberg Pool all the way to the falls is different all along the river. So let me just jump over here. We'll go back on the details of how the waves are generated by boats. So I was fortunate enough that about 2 years ago, maybe a year and a half ago, I was in a boat with some of, I was taken by a boat to see what is going on in that particular area of the river. And what was really striking to me is that every 50 meters, 50 yards, whatever, the riverbanks are different. We have artificial protection elements, if you like. Let's talk about the margins. We have artificial elements that are protecting the riverbanks, but also we have the other effect that we are not talking yet completely about what happens to those structures, the interaction of the waves and those structures. We have different elements along the the river. We have margins with riprap. This might be artificial or not. Sometimes it's natural, sometimes it's not. Sometimes we have sand, we have silt, we have debris, we have vegetation. One type of vegetation, another type of vegetation, one slope with different sizes, and this is changing every 50 yards or less. So it's practically impossible in this particular place to have a definite, unique solution of what's going on. Because we have to change our resolution from here to here. Every time. It's physically impossible. And that is because this is partly natural, partly artificial location when we are dealing with. And that's one of the things that I think makes this problem super complicated. Because we don't have a single answer for everything, except the zero solution. That's the only answer that we have for this. So there are more and more examples of places where we have erosion. The erosion itself may produce some debris that is protecting the bank, and then there is no problem anymore. Or erosion that may happen because of something else, because whatever happens there is not because of you, or the other way around. Whatever happens there is because of this. Anyway, so just when I was in the hearing, I don't know, a number of months ago, one of the messages that I wanted to give is that this is not a simple problem. This is, in this particular location, is so different, it's so variable on that side, that we were talking about the variability of how to predict or understand the erosion. That's what Desiree showed us. And I'm giving you an additional problem. It's like not only the variability of the process, but the variability of the different locations. So it's a massive, very complicated problem. So what the conclusion was, let's start identifying a causal relationship between what happens in terms of erosion or damage to dogs with the actual existence of those boats. How many boats we have, what are the characteristics of the boats, how we can correlate those boats into waves and erosion. So that is partly what we are doing, and it's partly what Solomon is going to explain to you how that works. And that was the intention of the whole presentation of what we are thinking that we should do at this moment. So, anyway, there's a number of other examples of different solutions on protection. So, for example, and again, this is just a selection of the images that I had during this relatively short trip that we did out of the Willamette. So everything is different. Every 5 meters is completely different. It's just all over the place. So, so that is one thing that I would like you to keep in mind. And I want to correlate that to, we understand that there is a variability on the understanding of how the banks are eroded, and also with the data that we may want, what we want to have. So we can have a policy that is based not on, there is a lot of variability and uncertainty on our predictions. There is information regarding not only the size of the waves, but also what is actually happening on the shorelines, and where we have more or less damage because of something else that is happening. The problem with that is that we need time. We need time to get that information, to gather that information and have something that is strong enough that over the years give us some picture of what is going on and how and where the erosion is higher, stronger, or more difficult to manage. So with this, before I let Professor Jim start with his presentation on weights, I would like to use this as an example of how we tend to understand things are working. And this is the first step. We would like to understand how things work. We say that we acknowledge that the waves are producing erosion, but the way we address this problem is by this scaling problem, this scaling in terms of size, so the space, and the time. So when we have a river like this, we have a flow that is fundamentally going in the direction of the river. So that is what Desiree showed, that we have continuous flow in this direction. That produces erosion. Naturally, the system will try to go to an equilibrium. The equilibrium is anything that goes, that is, if we make this wider, our velocities are going to go slower. And if my velocity goes slower, my stresses are slower, and then my ability to transport sediment is going to be reduced. And if I reduce my ability to transport sediment, the sediment will settle. So the river will become narrower. But if I go narrower, the velocity is going to increase. If I increase the velocity, my stresses are going to increase, and then I have erosion. So there is a sweet spot in between. That depends on that velocity of the river flow, the water depth, and the characteristics of the sediment. That process tends to an equilibrium, it's natural equilibrium, and happens in the long term. We're talking about several years, maybe more than several years, we may maybe talk about centuries to have an equilibrium condition. And as an engineer, and I remember what we measured in the laboratory, we want to simplify, and we don't have much, we want to keep things as simple as possible. That process is one scale, this process is another scale. So now I'm a boat, I'm producing waves. Those waves are hitting the shoreline in a cross direction, so we now, instead of looking in this direction, we look in this direction. And those waves, when they arrive to the shoreline, and similar to the beach that we saw on the flume, we have a process that has this time scale of the waves. So we are talking about a few seconds. A few seconds with enough current that is able to change the profile of my banks. That process is relatively short in time, and is limited to the location where my waves are reaching. So if I understand how these waves goes from here to there, then I may understand what happens to the bank, but locally in each of these locations. So if I understand the waves, I know what happens to the bank. And I can correlate that with different banks. If this bank is different from this, but I have the same wave, I can estimate what it would be the effect of this erosion, or the difference between the erosion here and the erosion here. So the way we treat it, and the way it's being explained, and you will see later, is that fundamentally we talk about one thing is this, the longshore direction transport, and what is this, which has a long-term, relatively equilibrium state natural condition. And that's the argument of some of the part of the industry, that is erosion is happening naturally. And the other component, which is the cross-shore transport. So an analysis that goes in the direction across the margins. So that's why we want to, or I would like to, as an engineer or scientist, try to address the problem. If I know how this is produced by this boat, and I get a correlation of that erosion, I may be able to assess or predict how that damage happens in the shore. And even I can go with different types of shore. So my idea or our proposal was, can we do a survey that is long-term that tells us that information? We have a boat, we know how that boat produces those waves, how those waves reach the coast, and how that erosion produces, how that boat waves produces erosion in the shoreline. And we can also include the effect of the docks. So the same way we produce some forces, it will transfer some energy into the docks, some motions, and those motions will damage or not the effect of those waves. So that is my interest in how I frame this process. So last thing is a little bit of some terminology, because we've been talking about wave energy, we've been talking about how this goes. Then we have to go a little bit more in detail of how to describe a wave. And I think we shouldn't talk about the wave energy, because you will see that the same wave with the same size may produce different effects. And that's because the description of the wave energy is incomplete. We don't have all the picture of what is the wave with a single parameter, which is its height. We need to go beyond that of not only saying, okay, oh, I'm producing a wave that is 3 feet and I'm not producing damage, And this guy is producing a wave that is 2 feet, but is producing a lot of damage. You want to understand that is not because the wave energy is the only parameter that describes the process, is what we call the wave energy flux, which correlates also how long is that wave. So what is the distance between two successive waves, or what is the time between two successive waves is related. So we incorporate that parameter, we can see that the longer the wave, the more energy we have, the energy flux. So it's going to be more difficult for us to stop a truck that is 50 tons, that is going 10 miles an hour, than a little car, Ferrari, that is going 200 miles per hour. Because the weight of the Ferrari is small. So imagine the weight is the same as the wavelength of a wave. So to stop a Ferrari, we need a little thing, even if it's going 200 miles an hour. But to stop a truck that is 40 tons and is going 10 miles an hour, we can't. We just keep going. Same happens with the tsunami. The tsunami is relatively small in comparison to other waves that you find in the ocean. But to stop it, because it's super long, is very difficult. It has a lot of momentum in what it happens. So I would like to start getting in that vocabulary in everyone, is that it's not only the wave energy that matters in this case, it's also the wavelength. So in a way, the wave energy flux, how much momentum we are transferring to the system. It is different. If we have more momentum, it's going to be more difficult to stop it, there's going to be more damage, the currents are going to be stronger, and so on. Okay? Good? Yes?
You talk about a long-term study. What are we talking about time-wise?
I believe that we should include somehow the variability of the Willow tree. So that means at least 5 years.
During that time, we're talking about different shorelines and different erosion patterns. How will you study those in that period and still come up with some solutions? You have two types of problems. You have summer and winters, as far as I can tell. The winter is almost as damaging, perhaps, as the wave boats, or the boating altogether. And if some areas have a solution, how will that apply to all areas? So you really got to be really careful in your investigation. And if you're talking about the Willamette River, I think it's more than 100 miles long. And so we're going to be studying this, and it's not going to be even complete because the work that designated areas. I'm in a lake-free area. If I could provide some kind of shoreline protection from my area right now, I may not care what boats are on there. So there's going to have to be some alternatives for different areas. And I don't think that maybe riprap is the way to go in my particular area. But it might not apply to a lot of others.
So you're completely right. The good news there is that river margins and coastline have been protected already with different solutions, and each solution is more suitable for different places. So sometimes you talk about riprap, sometimes you talk about groins, sometimes you talk about, so those are the visual things. Sometimes there are soft solutions, which means nourishing sand. People just bring more sand and to